I need all of you to settle down quickly. There should be absolute silence in the classroom. I think there is, more noise coming from room 2. Yeah. Now I'll begin once, everyone is silent. Keep the mic on so that I'll be able to listen to them. Yeah. Okay, fine then. Let us begin with the topic. Now in kinematics, which you might have done in your 11th class, you might have dealt with motion in 1 dimension, 2 dimension, and in some cases motion in 3 dimension also. Now since today is the very first class, I will limit myself to the discussion of motion in 1 dimension, in which we will take a quick look at the 3 equations in kinematics and a very important aspect about the 3 equations in kinematics, and then take up a few examples before we go to the next class. Still there is continuous talking from room 2. Let us mute this. Right. Okay. Fine. Now, in kinematics, let us quickly take a look at few definitions. How do you define the distance of a point? Like suppose if someone asks you, what is the distance of Secunderabad? What would your answer be? Probably since you people are at Sholapur, you will quote certain, few hundred kilometers from your place. At the same time, if someone was to ask me as to what is the distance of Secunderabad, I would just probably say it is 6 kilometers. So if my answer is 6 kilometers and if someone else's answer is 600 kilometers, which of these two answers is correct? It is very important to understand in kinematics and to do some good quality numericals in dynamics and for the rest of the physics, that the first thing that we have to be very sure of is what we call as a frame of reference. It means you must be absolutely sure of from which point you are going to observe the body. Once that point is once that point is decided, then you can make your analysis about the motion of the body. So the first thing that we must know in kinematics is from where are we going to observe the motion. From where are we going to observe the motion? This is the first thing that we must know. Now, having decided upon the motion, like suppose, let us look at a small situation here. Suppose there is a tree, right? And suppose this is a horizontal road and there is an observer here. Suppose there is an observer here and he is observing, let us say, a small object here. For example, let us say it's a small trolley or something. He is observing the small trolley from his position. What is the importance of indicating a tree here? I don't mean to say that in all your diagrams you end up showing a tree every time you have to draw a diagram in kinematics. But at least in the beginning we do that. Now, why are we doing that? This is only to drive home the point that you are standing next to a tree and you are not moving and you haven't seen any trees moving around on earth. So for this small observation, you are observing the trolley from a stationary frame of reference. It means your reference frame is from here. From here you are measuring the distance of the trolley, and you could say that the distance of the trolley is 20 meters from your location. So you can say that the trolley is at a distance of 20 meters from you. Likewise, there could be your friend who could be standing behind the tree and he could also be stationary. Suppose there is another friend. So this is person A and this is person B. So suppose there is another person. and he also observes the trolley. Then he would say that the trolley is at a distance of 30 meters. So now the question is, who is correct? And the answer is both of them are correct. Both of them are correct independently from their own points of observation. Therefore, from where do you observe the body is very important. Now, in kinematics, of course, as we proceed further with classes, we'll be looking at a very concrete vector notation of addressing problems related to kinematics. But let us make a brief mention of that, even though we are going to speak of only one-dimensional motion for today's class and for a couple of classes from now. Still, let us be very sure of the notation. I hope you people are familiar with this notation of vectors being indicated with I cap, J cap, and just a minute, let me edit this. Yeah, J caps and K caps. Now, since there was certain amount of noise coming from one of the rooms, I have muted the mics there. If you know this notation of I cap, J caps, and K caps, please raise your hand so that I come to know whether you are familiar with it or not. If you are familiar with the notation of I caps, J caps, K caps, please raise your hands very clearly so that I can see that. 1, 2, 3, 4, about 5 or 6 from room 1 and 1 or 2 from room 2. Okay, fine. So now, in order to take everyone into the account, let us spend some time for I, J, K caps, and then we'll come back to this problem, because it's very important to have our direction of vectors and the information regarding the direction of vectors in place, because vectors are like tools for addressing any problem in physics, and for that matter quite a few problems in mathematics also. I'll give you an example for this. Suppose a friend of yours happens to come to Secunderabad or Hyderabad, and because I'm stationed here, I'll continue to take that example. Suppose a friend of yours comes to Secunderabad and he wants to come to my house, for example. And he walks out of the gate of Secunderabad railway station and he says, "Sir, I have reached Secunderabad, and how many kilometers is your house from here?" I say, "Yeah, it's very easy, exactly 10 kilometers from where you are standing, and my house is there." So he immediately comes out, takes a right-hand side turn, and he walks 10 kilometers. Naturally, he is nowhere near my house, because probably what I meant to say was, it is 10 kilometers, but take the first left-hand side turn and you can walk straight. So the information of magnitude, that is 10 kilometers, is not just sufficient in all the situations. In some cases it is, in some cases it is not. So if you want to convey the complete meaning, then you must say 10 kilometers in so and so direction. Now, saying 10 kilometers in left hand side, 10 kilometers in right hand side, or 10 kilometers forward is also not a very correct way, because suppose it is not 10 kilometers left hand side, it is not 10 kilometers right hand side, it is not 10 kilometers forward, it is 10 kilometers along a diagonal road. Then how do you express that? Therefore, a concrete mathematical technique has to be developed. We are going to speak of cars approaching each other. We are going to speak of cars following each other. We are going to speak of bodies being dropped from a certain height. And we are going to speak of bodies which are dropped from a certain height and simultaneously another body is projected up. Where do they meet? After how much time do they meet? What is the relative velocity? So in all these problems, you must be absolutely sure of magnitude and direction. Only then you will be able to solve the problems. So keeping that in mind, let us start developing the vector notation from a very early stage itself. So in the use of vectors, we say that the entire space can be understood by using 3 directions. One is X, one is Y, and one is coming towards you. This is Z, right? So suppose this is the X axis, this is the Y axis, then this is the Z axis. Angle between X and Y axis is 90 degrees, angle between Y and Z axis is 90 degrees, and angle between Z and X axis is also 90 degrees. So this is 90 degrees, this is 90 degrees, and this is also 90 degrees. You will need this information once we address 2-dimensional and 3-dimensional problems. Presently, our job is to only understand what is I, J, K cap, but since there are J and K's also, I am drawing this diagram. So let us extend this diagram backward also. So this is, let us say, negative x-axis. This was positive x-axis, this is negative x-axis. And this is the negative y-axis. And here you have the negative z-axis going back like this. So you have x-axis, y-axis and z-axis. You are free to choose x-axis in whichever direction you want. You are free to choose y-axis also in whichever direction you want. But once you fix these two, you are not free to choose z-axis in whichever direction you want. Z-axis should be perpendicular to the plane containing x and y-axis. That is rule number 1. And rule number 2 is, if you point your right hand fingers along x-axis and turn them towards the y-axis, then the direction of thumb should be positive z-axis. There is no other possibility for that. This is the way we fix x, y, z axis. Right? I hope this is clear to you. Right? We'll be coming across this quite a number of times, but then just do remember it. X-axis can be taken in any direction. Y-axis can be taken in any direction. Once you fix x and y-axis, z direction, the direction of z-axis is uniquely defined. You can't just arbitrarily draw any direction and say that this is z-axis. That can't be done. Right. So, if you want to say that you are considering a position of 20 meters from your point of observation in the positive x direction, then how do you indicate that? Let us say that the person A is you right now. So this is the origin. So this here is the x-axis, and right passing through you, I'm not able to draw this very straight, but I hope you understand the point here. Yeah, this is the y-axis and this is the z-axis. Notice that the xyz axis that I have drawn here, I have just redrawn it here once again for our reference, because we are there always. The origin should be from where you are going to observe the body. So from your point of origin, the body is along the positive x-axis direction at a distance of 20 meters. This entire information can be conveyed by writing it like this: S bar is equal to 20, I'll just write this once again, yeah, 20 I cap. This notation has two parts. There is an I cap and there is 20 here. 20 indicates the magnitude, it means how far. I cap indicates the direction, in which direction. So vector, you have learned till now that vector is a quantity which has got magnitude and direction. Scalar is a quantity which has got only magnitude but no direction, or direction need not be specified for that. And here you see a very concrete mathematical technique being used just to denote the fact that displacement is a vector. 20 units along I direction, that's it. So how will you write if there is another car in this direction and you want to observe it, and suppose there is another car here, or there is a box kept here. Suppose there is a box kept here and this is at a distance of, let us say, 26 meters. Then how would you write that? You will say displacement or position of the box is, what will you write here? 26 meters. But I cap is towards right hand side. Now this is towards left hand side. So you will write minus I cap. I hope this is clear to you now. This minus can be pulled outside and you can write, let me drag this a bit down. Yeah. So now you can write this position of the box is minus 26 I cap. Right. So this is how you can write the positions of objects which are along x-axis. The same thing can be done for y-axis and the same thing can be done for z-axis also. Now if the body is somewhere in between x-axis and y-axis, suppose the body is somewhere in between. For example, suppose you are standing here, or let me clear off everything. I'll just see how to clear off all this. Clear my annotations. Yeah, fine. So now let us come back to this. Yeah. It's been a long time, so I'm kind of searching for my pencil tool and eraser tool. I hope you will excuse me for that. In a couple of classes I'll get used to this and it will be really fast, I hope. right? Okay. Now suppose you are again on a ground like this, right? And there is a tree here, right? There is a tree here, and you are observing not the tree but something on the tree. So suppose there is a small apple. Apple fell on Newton's head. There is a story about that. But actually, apple did not fall on Newton's head. I'll come back to that when I'm